Quantities that can be measured are called physical quantities. Physical quantities include length, mass, time, temperature, etc. For example, when we measure the length of a cricket pitch using a measuring tape, or when a person measures the weight of a fruit using a digital scale, they are working with physical quantities. So any property of an object that we can measure is a physical quantity. Physical quantities are divided into two main types: fundamental quantities and derived quantities. Fundamental quantities are basic. There are only 7 of them. You might be already familiar with length, mass, and time. These quantities, the fundamental quantities, they are independent and cannot be broken down into anything simpler. We measure them using the SI system of units. Derived quantities are formed by combining two or more fundamental quantities. For example, speed is a derived quantity because it comes from dividing distance by time. So, fundamental quantities are the building blocks and derived quantities are built from them. Now let's take a closer look at the fundamental quantities and their corresponding SI units. These are the basic quantities we measure and each has its own unit. Length is measured in meters. Mass is measured in kilograms. Time is measured in seconds. Temperature is measured in Kelvin. Electric current is measured in amperes. Luminous intensity is measured in candelas. Amount of substance is measured in moles. Each physical quantity has a symbol that is used to represent it in equations. Here is a table summarizing the physical quantities, SI units, and their symbols. Now here is a piece of cloth. Imagine that this piece of cloth is 10 meters long. When we say that the length is 10 meters, what that really means is that the standard unit meter fits into the cloth's total length 10 times. So if we break down this length, it's like repeating the 1 meter length 10 times as shown here at the bottom. Each section represents 1 meter, and when we count them, we get the total length of 10 meters. This is a simple way of breaking down lengths using standard units. Now let's look at mass. Here we have a bag of sugar that weighs 5 kilograms. The standard unit we use for mass is kilogram. And in this case, the 5 kilograms means that the kilogram unit is repeated 5 times within the total mass of the sugar. To help visualize this, we can see 5 separate bowls of sugar, each containing 1 kilogram. When we add them together, we get the total mass of 5 kilograms as marked on the sugar bag. Just like with length, the kilogram is a standard unit and it is shown 5 times to represent the total mass of sugar. These examples help us understand how measurements work with standard units. Whether we are measuring length or mass, breaking things down into standard units helps us understand and compare different quantities more easily. Types of units we often work with: fundamental units and derived units. Fundamental units, as I described before, are the basic units that are independent of any other unit. Examples of fundamental units include mass, length, time, temperature, luminous intensity, electric current, amount of a substance. These are the core units that we start with when we talk about measurements. Derived units, on the other hand, depend on fundamental units. They are expressed in terms of fundamental units. For example, area, volume, speed, Force, pressure, density, acceleration, all these are derived units because they are calculated from combinations of fundamental units like length and time. Now let's look at an example of derived unit in action. The area of a square is a derived unit. Area is found by multiplying the length by the length. If we write this mathematically, area of square is equal to length multiplied by length, or in terms of units, area is equal to meters multiplied by meters. Okay, so length is measured in meters. So meter multiplied by meters gives us meter squared. Similarly, volume of cube is another example of a derived unit. It's calculated by multiplying the length by itself 3 times. Length multiplied by length multiplied by length, resulting in a unit of meter cube. So as we can see, derived units come from combination of fundamental units, and they help us measure more complex quantities like area and volume. Speed is a physical quantity that tells us how fast or slow something is moving. The formula for speed is equal to distance divided by time. The unit for distance is meters and the unit for time is seconds. So the derived unit for speed is meters per second. This means that speed is measured in terms of how far something travels in 1 second. Meters per second. It is a derived unit which uses the fundamental units of length and time.
Derived units are units that are formed by combining the basic or fundamental units of measurement like meters, seconds, and kilograms. Now let's look at a few common examples. Area. Area is calculated by multiplying length and breadth. So its derived unit is meter multiplied by meter, which gives us meter squared, symbolized as m squared. So that is meter square. Then comes volume. Volume extends the concept of area by adding height. So it is length multiplied by breadth multiplied by height. That gives us meter multiplied by meter multiplied by meter, or cubic meter. Density. Density is defined as mass divided by volume. Mass is measured in kilograms and volume, as we just saw, is in cubic meters. So the derived unit becomes kilogram per meter cube, or kilogram per cubic meter. Speed is how fast something is moving, and it is defined as distance divided by time. Derived unit is meter per second. Acceleration is the change in speed divided by time. That means it's meter per second, or we can write it as meters per second squared. So, in summary, by combining fundamental units in different ways, we get new units called derived units. Before we end today's session, let's quickly recap what we have learned. First of all, we learned that quantities that can be measured are called fundamental quantities. These include length, mass, time, temperature, etc. Next, we saw that physical quantities are divided into two categories: fundamental quantities and derived quantities. Then, we discussed that physical quantities are measured using the SI system, which stands for International System of Units. This is a standard system used all over the world. The SI system is built on 7 fundamental quantities. These are the basic building blocks from which other quantities are derived. Finally, we understood that any physical quantity that is defined using these fundamental quantities is called a derived quantity. Examples include area, volume, speed, and density.
Area. Area is the amount of surface covered by a closed shape. The standard SI unit of area is square meters, written as meter squared. It's a derived quantity, just like volume. Volume is measured in cubic meters. For small objects, we use square centimeters, while for larger areas, we use square kilometers or hectares. When measuring very large surfaces like agricultural land, we use a unit called hectare. 1 hectare is equal to 10,000 square meters. Let's look at a smaller object, a sheet of paper. If we calculate the area using its dimensions, 21 centimeter by 29.7 centimeters, we get an area of 623.7 square centimeters. If we convert that to square kilometers, it becomes a very tiny decimal, 0.0000006237 kilometers square, which is not practical to use in daily life. That's why we stick to units like centimeter square for smaller objects. Now, what about surfaces that don't have regular shapes, like this hand? Can we still find the area? Yes, but how? We can use the graph paper to estimate the area by counting the number of squares the shape covers. Let's learn how to convert square centimeters to square meters. We start with 1 centimeter square is equal to 1 centimeter multiplied by 1 centimeter. We know that 1 centimeter is equal to 1 by 100 of a meter. So 1 by 100 meters multiplied by 1 by 100 meters. This would be 1 by 10,000 meter square. So 1 centimeter square is equal to 0.0001 meter square. So whenever you are converting centimeter square to meter square, just divide by 10,000. Now let's convert kilometer square to meter square. 1 kilometer equals 1000 meters. So I can just write 1 kilometer square is 1 kilometer multiplied by 1 kilometer. 1 kilometer is 1000 meters. So 1000 meter multiplied by 1000 meter. So this is 10 raised to 6. 10 lakhs meter square. Now, what about hectares? A hectare is a unit often used to measure land. 1 hectare is a square that is 100 meters on each side. To remember hectares, just imagine a square having length of 100 meters and 100 meters. So 100 multiplied by 100 meters would give you 10,000 meter square. So 1 hectare is 10,000 square meters. So this is an easy way to remember hectares. Now let's convert 1000 square meters to square kilometers. We know that 1 square kilometer is equal to 10 lakhs, 10 raised to 6, 1 million meter square. Therefore, 1000 meter square would be equal to 1000 divided by 10 to the power 6. So, the answer would be equal to 0.001 kilometer square. So, when going from a smaller unit to a bigger one, we divide. Let's convert 64 square centimeters into square meters. We know that 1 centimeter square is 0.0001 meter square. So to convert 64 centimeter square, we multiply 64 by 0.0001 and the answer will be 0.0064 meter square. So this is the area in square meters. Now let's try a bigger number. We are converting 432 centimeter square to meter square. 1 centimeter square is 0.0001 meter square. So let's multiply 432 by 0.001. The answer will be 0.0432 meter square. Let's learn how to find the area of regular shapes. These are shapes with fixed sides and known formula. For a square, area is side multiplied by side. For a rectangle, area is length multiplied by breadth. For a triangle, we use half multiplied by base multiplied by height. And for a circle, the area is pi r squared. Pi multiplied by square of the radius. So these formulas help us quickly calculate area when we know the dimensions. You can look at this table. Area of square, rectangle, triangle and circle can be calculated using this formula. Area is side multiplied by side for square, area is length multiplied by breadth for rectangle, area is half base into height for triangle, and area is pi r square for circle. Here is a real life example. Rohini has a square piece of colored paper for a class project. The length of each side of the square is 8 centimeter. What's the area of the paper? Convert the answer to meter square. So we multiply side by side. Side multiplied by side will give you 64 centimeter square. Now to convert this into square meters, we multiply it by 0.0001. So the answer is 0.0064 meter square. That's the area of her paper. Siju wants to measure area covered by his rectangular notebook. If the notebook is 24 centimeters long and 18 centimeters wide, what is its area? Convert the answer to meter square. Now let's look at a rectangle here. Okay, so 24 centimeter long, 18 centimeter wide. So we multiply length by breadth. 24 multiplied by 18 is 432 centimeter square. Let's convert it to square meters. Multiplied by 0.0001. And the answer is 0.0432 meter square. That's the area of his notebook in square meters. Not all shapes are regular. Some, like leaves or palms, don't have straight sides or a standard shape. These are called irregular shapes. We can still find their area using a grid of square centimeters. So we place the shape on the grid and count the number of squares it covers to get an approximate area. So I am repeating. We can find their area using a grid of square centimeters. We place the shape on the grid and count the number of squares it covers to get an approximate area. When dealing with irregular shapes, we often use square centimeter grid to estimate the area. Each square on the grid is 1 centimeter multiplied by 1 centimeter, so its area is 1 centimeter square. To estimate the total area, we can use this trick. Count all the full squares. First you will count all the full squares and then add half or more than half squares. Again, count all full squares and then add half or more than half squares. Then multiply the total by 1 centimeter square to get an approximate area. Let's compare area and volume. Area is the amount of surface covered by a two-dimensional shape like a square or rectangle. It's measured in square units. Now see, this is the definition: amount of surface covered by a closed shape. Volume, it is the amount of space occupied by an object. So plane figures are two-dimensional, solids are three-dimensional. Formula is length multiplied by breadth, whereas for volume we also take into consideration the height. Unit would be in square units: centimeter square, meter square, kilometer square, and for volume it would be cubic units: centimeter cube, meter cube. So you can see examples of 3D objects like this red cube and blue cylinder. These shapes not only have length and breadth but also height or depth. So when we calculate their volume, we multiply length, breadth and height. So this tells us how much space the object takes up.
What did we learn in this session? Area is the amount of surface covered by a closed shape, measured in units like centimeter square, meter square and hectares depending on size. Unit conversions are essential for solving real-world area problems. Regular shapes such as square, rectangle, triangle, circle. Such regular shapes have specific formula for calculation of area. Irregular shapes can be estimated using graph paper by counting full or partial squares. So finally, area measures surface while volume measures the space inside 3D objects. Volume. Volume is the amount of space occupied by an object. Look at the two objects on the screen: an eraser and a book. Which one takes up more space? Yes, the book. So we say the book has more volume and the eraser has less volume. Remember, bigger objects usually have more volume because they occupy more space. Here is another example. We have a bucket full of water and a water bottle. The bucket is bigger and holds more water, so it has more volume. The bottle is smaller and holds less water, so it has less volume. So again, volume tells us how much space something takes up, whether it's solid or liquid. Now let's compare these two circular objects: a motorbike tire and a bicycle wheel. Even though both are round, the tire is thicker and bulkier, so it has more volume. The bicycle wheel is thinner and mostly with little air inside it, in the tube that you can see along the perimeter of the wheel. So it has less volume. So it's not just the shape but the space inside an object that tells us about its volume. Now that we understand what volume is, let's talk about how we measure it. The SI unit of volume is cubic meter. This cube here shows that it's 1 meter long, 1 meter wide and 1 meter high. So the volume is length multiplied by breadth multiplied by height, which is 1 meter multiplied by 1 meter multiplied by 1 meter equal to 1 meter cube or 1 cubic meter. This is called a unit volume. It's the standard reference for measuring the volume of any object in the SI system. Now, let's apply this idea to real life spaces. Take a look at this room. It's a space that occupies volume, just like the cube. We can measure the room's volume using the same formula. Length multiplied by breadth multiplied by height. And the answer will be in cubic meters. So whenever we want to calculate the amount of space inside a room, we measure its volume in meter cube. Here is another example, a tank. A tank is used to store water, and we need to know how much it can hold. This is measured by its volume. We can measure it in cubic meters. Even though the shape of the tank is cylindrical, we still use the volume formula to calculate how much water it can contain. So whether it's a cube, a room, or a tank, the space they occupy is always measured in meter cube. Now let's talk about how we measure volume of smaller solid objects like a brick. Just like the big cube that we saw earlier, we use this formula. Volume is equal to length into breadth into height. And in this case, the dimensions are given 24 centimeters multiplied by 10 centimeters multiplied by the height, which is 7 centimeters. So the volume is 1680 centimeter cube or 1680 cubic centimeters. So we use cubic centimeters for smaller solid objects like bricks, boxes, or books. Volume of a liquid. We don't measure liquids usually in cubic centimeters. We use liters. We are more familiar with this unit when we are measuring liquid. So here are some examples. A small bottle of hand wash might hold 250 milliliters. A water spray bottle could be 750 milliliters or even 1 liter. A detergent container might be 3 liters or even 5 liters. So the volume of a liquid tells us how much space it takes up, and we usually write it in liters or milliliters. For smaller amounts of liquid, we use milliliters. Here we can see a measuring beaker. One shows 40 ml and another shows 75 ml. And the flask on the right has 200 ml of liquid. 1000 milliliters, please remember this. 1000 milliliters is equal to 1 liter. So when we are dealing with small quantities, we usually use ml, milliliters. And when we are talking about larger quantities, we use liters. Let's now understand how different volume units relate to each other. We will start with converting cubic meters to cubic centimeters. We know that 1 meter is equal to 100 centimeters. So, 1 cubic meter is equal to 100 centimeter multiplied by 100 centimeter multiplied by 100 centimeter. So that is 100 centimeter cube. That gives us 100,000. cubic centimeters. So 1 meter cube is equal to 10 raised to 6 centimeter cube. Or you can say that a cubic meter is a very large unit and it's made up of 1,000,000 cubic centimeters. Now let's look at something simpler. Milliliters and cubic centimeters. You will be happy to know that 1 milliliter is equal to 1 cubic centimeter. That's right. If you see 100 milliliters of water, it's the same as 100 centimeter cube. Now let's connect liters with cubic centimeters. 1 liter is equal to 1000 milliliters and 1 milliliter is equal to 1 centimeter cube. So that means that 1 liter is equal to 1000 centimeter cube. So 1 liter of any liquid takes up the same space as 1000 cubic centimeters. This helps us switch between solid and liquid volume units easily. Now let's see how liters are converted into cubic meters. We know that 1 liter is 1000 cubic centimeters. And 1 meter cube is 10 raised to 6 centimeter cube. To convert liters to cubic meters, we divide 1000 by 10 raised to 6. So this would give us 0.001 meter cube. So 1 liter is equal to 0.001 cubic meters. This is useful when we deal with large liquid quantities. Now let's reverse the conversion from cubic meters to liters. 1 meter cube is 10 raised to 6 centimeter cube. You can see 6 zeros here. And 1 liter is 1000 centimeter cube. So let's divide this. 1 meter cube is equal to 10 raised to 6 divided by 10 raised to 3. This gives us 1000 liters. This shows that a cubic meter is a very large unit. It can hold 1000 liters of liquid. Let's find the volume of a cube. A cube has all sides equal. So the formula is volume equal to length multiplied by length multiplied by length. Now let's look at another shape, the cuboid. Cuboid is like a box. It has different lengths, widths and heights. To find the volume of this cuboid, we will use the formula volume equal to length multiplied by breadth multiplied by height. So just multiply all three sides and you will get the volume in cubic units like centimeter cube or meter cube. This formula works for many regular objects like books, bricks and shoeboxes. But what happens when the object is not a regular shape? Look at this rock. It's an irregular solid, which means it has no fixed shape and no easy formula to calculate its volume. So if I ask you, what is the volume of this rock? We don't have any formula for this. So What will we do? Let's find out. For irregular solids like a stone, we use the water displacement method. Of course, the stone we are using is much smaller than the one I showed you in the previous slide. Here is how this water displacement method works. Fill a measuring cylinder with water and note the level. Carefully drop this irregular solid into water. Now what will happen? The water level rises. The increase in water level tells us the volume of the object. So if the water level rises from 150 milliliters to 200 milliliters, let's say, it's less here, but it rises, let's say from 150 to 200. The volume would be 200 minus 150. That would give us 50 milliliters. So this method is very useful in labs and science experiments when dealing with odd shaped objects. Okay, we can say irregular objects. So increase in volume provides the volume of solid. You can look at this animation to understand how this works. You can see the increase in volume, and that increase in volume is the volume of the solid. Now let's understand the difference between two important terms, capacity and volume. On the left side we see capacity, and on the right side we see volume. Capacity is the maximum amount a container can hold. For example, this beaker has a total capacity of 100 milliliters. It's filled to the top. You might argue we can still fill a bit more. I agree with you. So of the maximum amount, a maximum amount a container can hold is capacity. And on the right side, we are seeing volume. It's the actual amount of space occupied by something. In this case, the liquid inside the beaker. It is the amount that it currently holds. So beaker is only filled up to 60 milliliters. So volume of liquid is 60 milliliters. So in simple words, capacity is about the container, how much it can hold. Volume is about the content, how much it is holding right now. I am repeating this. Capacity is about the container, how much it can hold. And volume is about content, how much it is holding right now. Both are measured in the same units like liters or milliliters, but they tell us different things. So, what did we learn in this session? We learned that volume is the amount of space occupied by an object. The SI unit of volume is cubic meters, and smaller volumes use centimeter cube, milliliters, or even liters. Volume of regular solids like cubes and cuboids can be calculated using formula, whereas volume of irregular solids can be measured using water displacement method. Then capacity is the maximum amount a container can hold, while volume is what it currently holds.
Density. We are going to explore an important concept in physics and everyday life, density. So what is density? Density is defined as mass of a substance per unit volume. In simple words, it tells us how tightly packed the particles are inside an object or a material. Let's look at these two cubes. One is made of wood and the other is made of steel. Now here is something interesting. Both cubes are exactly the same size. They each have a volume of 1 cubic meter. That means they take up the same amount of space. But when we look at their masses, things start to look different. The wooden cube has a mass of 700 kilograms, while the steel cube has a mass of 8,000 kilograms. That's a big difference. So even though the size is the same, the steel cube is much heavier. Why? Because the particles in steel are packed much more tightly than those in wood. This is where density comes into play, and we will calculate it in the next slide. Let's now calculate the density of both cubes using the formula density equal to mass divided by volume. Let's start with the wooden cube. Mass is 700 kilogram, volume is 1 meter cube, so density is 700 divided by 1, which is 700 kilograms per cubic meter. Now for the steel cube, mass is 8,000 kilogram, volume is 1 meter cube, so density is 8,000 divided by 1, which is 8,000 kilograms per cubic meter. So what do we observe? Even though both cubes are the same size, the steel cube has a much higher density. That's why it's so much heavier. It has more matter packed into every bit of space. So this is how density works. It helps us compare different materials even when they are the same size. Let's try another example, this time with cotton and sand. Again, we are looking at equal volumes. Each material takes up 1 cubic meter. But when we check their masses, cotton has a mass of 80 kilograms, sand has a mass of 1440 kilograms. Let's plug the numbers into our density formula. Density is mass divided by volume. So density of cotton is equal to 80 divided by 1, which is 80 kilogram per meter cube, and density of sand is 1440 kilogram per meter cube. So what do we notice? Cotton is much lighter and less dense. Its particles are loosely packed and there is more air in between. Sand, on the other hand, is made of tiny grains that fit together tightly, so it has a much higher density. Even though both materials occupy the same amount of space, sand has more mass, which means it is denser. So next time you pick up a bag of cotton and a bag of sand, remember, they may have the same volume, but density tells us how much stuff is actually packed inside. Alright, let's begin with something you've probably seen before. Here we have an iron nail dropped into water. What happens? When an iron nail is dropped into water, it would sink. Let's ask why. The key idea here is density. The density of iron nail is much greater than the density of water. That means the iron nail is heavier. Iron nail is heavier for its size compared to water, so it sinks. So even though the iron nail is small, the matter inside it is tightly packed, making it dense. Because it's more dense than water, it doesn't float. It goes straight down. But now here is something that seems like a mystery. We just saw an iron nail sink, and now we have an iron ship, which is much bigger and much heavier, and guess what? The ship floats. How can that happen? It's made of iron too, right? Well, the answer lies in the design of the ship and how density works with volume. Let's look closer in the next slide. Here is a reason a huge iron ship floats while a small iron nail sinks. Okay, ship is not just a solid block of iron. It's built with a lot of hollow spaces, and those spaces are filled with air. So when we calculate the ship's density, we don't just consider the iron, we also include all that empty space inside. Let's use the formula again. Density is equal to mass divided by volume. Because the ship has a very large volume, the volume of the iron plus the volume of air, the overall density decreases. Yes, the overall density of the ship is less. Even though it's made of iron, the average density of the entire ship becomes less than the density of water, and that's why the ship floats. This is a perfect example of how shape, design, and air spaces can change an object's ability to float, even if it is made of a very heavy material like iron. Let's begin with a simple way to remember the formula for density. We use this helpful triangle with three parts: mass at the top, and at the bottom we have density and volume. How does this triangle work? If you want to find density, cover the word density in the triangle. You will see density is mass divided by volume. If you want to find mass, cover mass. So mass will be equal to density multiplied by volume. And finally, if you want to find volume, cover volume, and you will get mass divided by density. This triangle is a quick and easy tool to remember all three forms of the formula. Now that we understand the formula, let's talk about units. In science, we use standard units for measurement. And when it comes to density, there are two commonly used systems: the SI unit, which is used in most of the world, and in physics, it's kilogram per cubic meter. The CGS unit is centimeter gram second system, CGS, and the unit for density is gram per centimeter cube. CGS stands for centimeter gram second. So even though the two units measure the same thing, density, they use different base units for mass and volume. Let's learn how to convert between these two systems. We start with some basic conversions. 1 kilogram is 1000 grams. 1 cubic meter is 100 multiplied by 100 multiplied by 100 centimeters. So this would be 10 raised to 6 centimeter cube. You can see there would be 6 zeros here. So if we want to convert 1 kilogram per meter cube to gram per centimeter cube, we follow these steps, and finally we will get 1 kilogram per meter cube is 1 by 1000 gram per centimeter cube. Now let's do the reverse, converting from gram per centimeter cube to kilogram per meter cube. We know from earlier that 1 kilogram per meter cube is equal to 1 by 1000 gram per centimeter cube. So 1 gram per centimeter cube would be equal to, yes, 1000 kilogram per. Let's say you have a shiny golden object and you want to check if it's made of real gold. One scientific way to check is by using density. We know that the density of pure gold is 19.32 grams per cubic centimeter. So here is what we do. First we measure the mass of the object. Let's say the mass is 193 grams. Next we submerge it in water and measure how much water is displaced. That gives us the volume of the object, which is 10 centimeter cube. So 1 ml is 1 centimeter cube. Now using our formula density equal to mass divided by volume, we would get the density equal to 19.3 grams per centimeter cube. That's almost exactly the same as pure gold's density. So based on this density, we can say that this object could be real gold. Let's try another example. This time we have a different object. Its mass is 340 grams and it displaces 20 centimeter cube of water. Okay. So mass of the object is 340 grams. The volume of water displaced is 20 milliliter, which is equal to 20 centimeter cube. Density of object is mass divided by volume, and the density is 17 gram per centimeter cube. Now remember, real gold has a density of 19.32 grams per centimeter cube. This object is quite a bit less dense than real gold. That means that this object cannot be made of pure gold. It's either fake or mixed with other lighter materials. Conclusion is, this is not real gold based on its density. Let's taste one more object. The mass is 168 grams. It displaces 10 centimeter cube of water. Using the density formula, we get the value of density equal to 16.8 grams per centimeter cube. Once again, this is much lower than gold's density of 19.32 gram per centimeter cube. So we can confidently say that this object is not gold either. This is a great example of how density helps us identify materials without even needing to cut them open or damage them. So if something is claimed to be gold, always check its density. It's one of the most reliable tests. Let's take a look at the densities of some common substances that we may encounter in everyday life. This table shows density values in 2 units, gram per centimeter cube and kilogram per meter cube, the SI unit. Let's go through a few examples. Ice has a density of 0.92 gram per centimeter cube or 920 kilogram per meter cube. This is why ice floats on water, because its density is lower than that of water. Coal varies a bit from 1.1 to 1.4 gram per centimeter cube depending on the type. That's 1100 to 1400 kilogram per meter cube. Aluminium, a light but strong metal, has a density of 2.7 gram per centimeter cube or 2700 kilogram per meter cube. Steel, much denser and heavier, ranges from 7.75 to 8.05 gram per centimeter cube, which is about 7750 to 8050 kilogram per meter cube. And copper, another common metal used in wiring and coins, has a density of between 8.3 and 9 gram per centimeter cube. So that is up to 9000 kilogram per meter cube. So what can we learn from this? Materials have very different densities, and by measuring or comparing density, we can identify substances, understand how they behave, and determine whether they will float, sink, or withstand a certain force. Let's start with a fascinating fact now. Do you know what the densest naturally occurring substance on Earth is? It's called osmium. It has a density of 22,500 kilograms per cubic meter. That means in a cube just 1 meter on each side, osmium would weigh more than 22 tons. It's a bluish white hard metal and one of the rarest elements on Earth. This shows how density can vary greatly from one material to other. Now let's learn how to calculate volume of regular solids. That's object with standard shapes like cube, cylinder, sphere. Here's a quick guide. For a rectangular block or cuboid, volume is length into breadth into height. For a cube, since all sides are equal, volume is side multiplied by side multiplied by side. For a cylinder, use this formula: pi multiplied by square of the radius multiplied by height. And for a sphere, it is 4 by 3 multiplied by pi multiplied by radius cube. The value of pi is 22 divided by 7. These formula are very useful when we calculate density, because you need both mass and volume. But what if the object doesn't have regular shape? In the previous slide, we saw the objects were having regular shape. Now, let's say the object is not having a regular shape. Can we calculate the density? Yes. A rock or a piece of metal with no clear edges are irregular in shape. In that case, we use the water displacement method to find the volume. Here is how it works. First, we pour water into a measuring cylinder and record the initial volume. Then we gently place irregular object into water. Water level rises. We record the final volume. The volume of the object is simply V2 minus V1. Then using a balance, we find the mass of the object. Finally, we calculate the density using the formula density is equal to mass divided by volume. So the increase in volume provides the volume of the solid. Then you just plug in this value into the formula density is equal to mass divided by volume to get the density value for this irregular solid. So let's summarize the process for measuring density of an irregular solid. Step 1, measure the initial volume before placing the object in water. Step 2, measure the final volume after the object is fully submerged. Step 3, calculate the volume of the object as V2 minus V1. Step 4, measure the mass m of the object using a balance. And step 5, plug it into the formula density is mass divided by volume. You can use this table to record your values for multiple trials. So this method is commonly used in science labs and helps us accurately find the density of any irregular object. So before we end today's session, let's quickly review the important things we learned about density. Density is the ratio of mass to volume. We use the formula density equal to mass divided by volume. This formula helps us compare how tightly packed matter is in different substances. Objects with the same volume can have different densities. Why? Because they might have different masses. A wooden cube and a steel cube of the same size will have very different densities. Steel is heavier because it's more tightly packed. Floating and sinking depend on density. If an object is denser than water, it will sink. If it's less dense than water, it will float. That's why ships float but nails sink. Then we can measure density for both regular and irregular objects. For regular shapes like cubes and cylinders, we use volume formula. For irregular shapes like rocks, we use the water displacement method to find volume. And finally, unit conversion is quite important. We learned that 1 gram per centimeter cube, 1 gram per cubic centimeter is equal to 1000 kilograms per cubic meter. This helps us when switching between CGS and SI units.
Speed. Let's begin by understanding what speed is. Speed gives us a measure of how fast or slow an object is moving, no matter which direction it's going in. It is a scalar quantity, which means it only tells us how much, not in what direction. Look at the image here of the tortoise and the hare. This classic story illustrates speed quite nicely. The hare moves quickly and covers more distance in less time, so we say it has a higher speed. The tortoise, on the other hand, moves slowly and takes longer to cover the same distance, so it has a lower speed. So whenever you notice something moving, whether it's a person walking, a car driving, or an animal running, what you are observing is speed in action. Now let's compare the speed of different objects. Take this example. The speed of the car is 16 meters per second. That means the car covers 16 meters every second. In contrast, the speed of the bicycle is only 4 meters per second. That tells us that this bicycle is slower. It only covers 4 meters in the same amount of time. So by comparing these two values, we can say that the car is moving faster than the bicycle. So higher speed values indicate faster motion. This is a practical way to understand speed in real life. Faster vehicles or people cover more distance in less time compared to slower ones. Let's understand the definition of speed and how we measure it. Speed of an object is defined as the distance traveled by it in unit time. It is calculated by using a simple formula: speed is equal to distance divided by time. This tells us that the speed of an object depends on how much distance it travels and how much time it takes to travel that distance. Speed is also known as the rate of change of distance. So SI unit is meter per second. This means how many meters something travels in 1 second. Sometimes we also express speed in kilometers per hour, especially when dealing with large distances like vehicles traveling on a road. Now let's look at how we convert units of speed. Often speed is given in kilometers per hour, but the SI unit of speed is meter per second. So we need a method to convert between these units. So to convert 1 kilometer per hour to meter per second, we usually follow these 3 steps. First, you convert kilometers to meters. 1 kilometer is 1000 meters. Step 2, convert hours to seconds. 1 hour is 3600 seconds. So now we have 1 kilometer per hour is equal to 1000 meters per 3600 seconds. 1000 meters divided by 3600 seconds. So on simplifying, we get 1 kilometer per hour is equal to 5 by 18 meters per second. So this is a very useful conversion factor to remember. So to convert kilometer per hour to meter per second, multiply by 5 by 18 or 0.278. 1 kilometer per hour is equal to 0.278 meters per second. Now let's reverse the process. How do we convert from meters per second to kilometers per hour? Yes, you might have already guessed the answer, 18 divided by 5. So let's follow these 3 steps. Convert meters to kilometer. So 1 meter is equal to 1 by 1000 kilometer. Convert seconds to hour. 1 second is 1 by 3600 hour. Final conversion. 1 meter per second is equal to 1 by 1000 divided by 1 by 3600. So you will get 18 divided by 5. 18 by 5. This is an exciting real-life example. The legendary sprinter Usain Bolt, who holds the world record in the 200-meter race. In one of his Olympic performances, he ran 200 meters